if you take these foundation models, proprietary models, and if you give it very simple images, like an image of two cardboard boxes, very plain, one is bigger, one is smaller, and you ask it to generate an image where we unstack these boxes. So once it unstacks, physical properties of the boxes change. They are not exactly the same boxes, their shapes might be deformed, their sizes might be different, and this is problematic.
All right, everyone. Welcome to another episode of the TWIML AI podcast. I am your host, Sam Charrington. Today, I'm joined by Munawar Hayat. Munawar is a researcher at Qualcomm AI Research. Before we get going, be sure to take a moment to hit that subscribe button wherever you're listening to today's show. Munawar, welcome to the podcast.
Hey, Sam. Thanks a lot. Thanks for having me.
I'm really looking forward to digging into our conversation. We're going to be talking about some of Qualcomm's papers on multimodal AI and visual AI from the recent NeurIPS conference. To get us started, I'd love to have you share a little bit about your background. How'd you get into the field?
So I did my PhD in 2015 from Australia. I got interested in computer vision, and I took some courses in my undergrad on image processing. That's what fascinated me. And during my PhD, I worked on visual analysis of facial data. And then afterwards, I have been contributing to mostly different subfields of computer vision. And and then after my PhD, I stayed in academia. I had a faculty position, and then I moved to Qualcomm in 2023.
What's your research focus at Qualcomm?
At Qualcomm, I have been mostly working on multimodal generative AI. So, on vision language models for understanding, generation, and retrieval. And those are the three areas where I have my papers at NeurIPS that I believe we are going to discuss deeply. So, when I joined Qualcomm, the first project I worked on was uh, making diffusion models run efficiently on Qualcomm hardware. That's a mobile phone. And we're generating images in under half a second. And then uh, we also worked on visual understanding. That's visual question and answering. Given an image and a question, a text question, we want to respond to the question. And for visual question answering, we also had a model running on Qualcomm hardware. Um, Basically, here in Qualcomm, I have been working primarily on multimodal generative AI, on generating visual content, understanding visual content, and also retrieving cross-modal information.
When you think about how the field has evolved over the past couple of years since you started there, like, what's most exciting for you about this moment right now?
I guess we have come a long way. For decades, we were focused on solving niche, very specific problems. Think of We spent so much time in just solving, classifying different objects from visual images, and and then we moved on quite a bit. But there is a lot to do, I guess, especially uh, in visual understanding and also in visual generation. In visual generation, physics-based generation, I guess we largely lack on that. And also in visual understanding, once we marry a vision model with a language model, there are lots of works that show that vision largely gets ignored and the language model takes over. And we are responding basically from the parametric memory of the language model and not by looking at the actual visual content.
When you talk about physics-based generation, what do you mean by that?
So physics aware generation, meaning we had a summation recently in which we observed that if you take these foundation models, proprietary models, and if you give it very simple images, like an image of two cardboard boxes, very plain, one is bigger, one is smaller, and you ask it to generate an image where we unstack these boxes. So while these models can generate very fancy images with intricate visual details, but a simple task like this, where we have very plain objects and we want them to unstack them. So once it unstacks, the physical properties of the boxes change. They are not exactly the same boxes. Their shapes might be deformed. Their sizes might be different, and this is problematic. Like in future, if you want the robots to work within human environments and they want to perform normal tasks, then they have to have understanding of the physical world. So simple tasks like how would an image look like if I open a drawer? So um, current models fail. They would hallucinate. They would maybe generate new objects in there, or once they open the drawer, its physical properties are going to be different. Humans are very much kind of accustomed to that kind of thing in our like we just get by those things very
Right,
easily,
right.
right? We can we can create a mental simulation once we're opening a drawer, for example, that the drawer is going to open this way, so I don't have to stand in its way. I have to position myself at a certain position, so when the drawer opens it doesn't hit me, and so on and so forth, and how much it's going to open. And we can predict affordances, like where do we uh, grab to open the drawer, and so on. So those kinds of things, while we take it for granted, and but for the current models, it's a major limitation. They can't tackle it reliably and robustly.
Now, some of those things, those challenges, when I hear them, strike me as being fairly solvable with more training data, like, affordances and like where a box is, where a drawer is movable from, like what are the handles, that kind of thing. Others strike me as more where we're lacking foundation like memory, for example, as a more robust structure in VLMs. How do you think about what, maybe what's lacking, or where kind of opportunity lies in terms of overcoming the challenges that you're outlining?
Exactly. I guess training data is a big has a big role to play. So for this task, it's not as simple as crawling the web and collecting large scale training data. We can collect image text pairs. We can even generate description of images. But even those descriptions, they don't carry the physics information, the physical properties of the objects. So the models can kind of implicitly learn those. So and that remains a challenge. So one thing we observed was during training of these models, which is generally done with paired image text data, like image and its description. So if we expand the description of the images, we do prompt expansion. And during that expansion, if we try to describe the physics of the object in the scene, it really helps. For example, if your task is to unstack boxes, and you describe it that unstack the boxes, keep their structure intact, keep the lids closed if they're closed, and make sure the physical sizes of them they stay the same.
It seems like here we're taking advantage of the fact that the L is a lot stronger in VLMs than the V.
That's exactly true. So, so that in itself, I guess it's a big challenge. So, I guess from Travel Darrell's group, there was a recent very interesting study where they show the vision models, the vision foundation models like Dino or Clip or SAM, and so they by themselves have very strong vision capabilities. A simple task like spatial correspondence. So if we have two images, one is and both of them are taken from slightly different viewpoint of the same scene, and if you ask which point in this image corresponds to which point in that image, So the standard vision models can solve this task fairly reliably, but then they show that once you combine the vision model with the language model, the performance of vision language models falls below chance. So which is very interesting. Like they kind of fail. So and this is what we observed as well, and this is one of our papers in NeurIPS that tries to tackle that to some extent. I don't claim it's a solved problem. We have a long way to go. Yeah.
And which of the papers is this?
So in this paper, we are basically we provide a systematic analysis of why do vision language models hallucinate. Um, And what we observe is we take intermediate representations of the vision tokens recontextualized while they go through the language model. And then we have pair data of the same image text pairs, and we have data of different image text pairs. So if you get the distribution of the similarity of image embeddings and the text embeddings in the embedding space of the language model, then for the distribution of the same versus not same, we would expect those to be disentangled. But instead, what we saw was that they were highly tangled, like there was huge overlap, and this kind of intrigued us. And we did some further analysis, and what we observed was as the so remember in vision language models we have vision tokens and text tokens. We concatenate them, and then vision and text tokens, they go through the language model. So while predicting the next token, we would expect that the language model would attend to the vision token. For example, if I ask what's the color of this box, so we would expect the box to be attended to, the visual tokens corresponding to the box to be highly attentive to. Or in other words, if we visualize the attention scores that we can easily do in the language model, we will see we'll expect that the attention scores corresponding to the visual tokens of the object of interest are higher. But what we observed instead was that was not the case. And this kind of intrigued us, and we wanted to dig deep and try to tackle this problem. And that's basically what our work uh, in NeurIPS does. So
And this specific paper is attention guided alignment in efficient vision language models.
that's exactly right. So how, the thing is, how do we solve that, right? So we made some right observations that vision is not being attended to, vision is not being paid attention to.
Just a question that just jumps out at me is, when we think about how language models are trained, they're trained on, lots and lots of textual data. Is, part of the challenge that these vision tokens somehow don't exhibit the same, patterns and distribution as text tokens, and the language model doesn't know what to do with them as easily as it does with text?
That's right. So if we see, we have a pre-trained language model, as you said, it's trained on large scale text only data. And that scale of the training data is much bigger. Think of trillions of tokens, 15 or 20 trillion tokens, even for the smaller models. And then we have a pre-trained vision encoder, which is pre-trained on, think of a billion image text pairs. And the embedding space of the vision encoder and the language are different because they were pre-trained entirely differently. We want to combine them together, and we do some alignment of the vision and the text. And this alignment is done on a very small scale data generally. Uh, so that's kind of, I think that's also that has a role to play. So you want to combine these two foundation models, pre-trained entirely differently, and then you're combining them, and the scale of the data that you're combining, and the quality of the data, and what kind of descriptions are in there, that has a huge role to play, and that is generally much less. Um, so and but so we observe that in some of the even benchmarks that exist for vision language model analysis, If we ignore the vision and only ask the question to the language model, and the responses we get just by using the language model and on purpose ignoring the vision part on these benchmarks, it's comparable to if you would feed the vision language model with both image and text image data as well. So there is a problem with the benchmarks that we have as a community, and then I guess there are recent vision centric benchmarks coming in. um, so for example, if you ask what's the color of an elephant, for that, the language model probably knows what the color of an elephant is. It doesn't really need to look at. So, yeah, training data and the way they're trained, that has a huge role to play. And um, to tackle it, what we observed was that we want to inject the visual information at different hierarchical levels of the language model, meaning language model has different layers or different blocks. It's a transformer with different blocks. So we interleave. So we interleave cross attention modules after every fourth block, for example, and this way, right from the beginning till end, every fourth block, we have a cross attention module through which we interject or we inject the visual information, visual tokens. So we make sure that visual tokens are there, and then the loss formulation we also change. So we make sure that the seminal region within, or the salient region within the vision, is being attended to through an additional auxiliary loss, apart from the standard next token prediction loss that's used to train these models. So,
And what is like, how do you articulate the intuition behind this loss?
think of if my question is, what is the color of the shirt of person sitting next to maybe a dog, right? So now we can get a segmentation mask of the person. That's easy to get with off-the-shelf segmentation models. And the intuition is attention scores for the visual tokens must be highest for the person, for the visual tokens corresponding to the person, because that's what the question is, right? And so if we ask a human to answer to that question, they would focus on that particular region. So uh, we get these segmentation masks, and we can come up with a loss formulation. We know where visual tokens are, and where we know where tokens corresponding to the question are the visual tokens. And then we know what was the attention score, what were the attention scores while responding to this question. So we can maximize the attention scores corresponding to the relevant visual tokens. So we basically do it via segmentation masks through a SAM like model.
Is that implemented as an auxiliary model, or is segmentation formulated as a loss component itself?
It's formulated as a loss component. The segmentation masks are computed offline because this is just part of the training. So at inference you don't need that. You can live without that. But during training, we have these segmentation masks computed offline, and then we can use these segmentation masks to compute the auxiliary loss.
How does that impact your computational performance at training time? You said at inference time, it isn't doesn't impact it.
That's a great question. Just because we are injecting the visual tokens through cross attention modules, and we're not concatenating them at the beginning. So if you think of, like, if m is your number of vision tokens and n is number of text tokens, uh, through standard design, your compute complexity through the self attention modules would be m plus n whole squared. But now, uh, because text tokens are being self-attended to, and vision tokens are being cross-attended to, our compute becomes much less. Text, if it's n squared plus mn, so it's much less than m plus n whole squared. So we observe that compared with a standard approach, the training is actually faster this way. Yes, actually, there is like an additional cost to compute these masks offline, but that is uh, that's not part. That's just done once. That's just inference.
And that n squared relationship, in terms of complexity, is one of the challenges in achieving large context for language models, VLMs. Does reducing that complexity allow you to do things in terms of longer context as well? Is that something that you've explored?
It does. We have explored. It's not part of the paper, but it's a continuing work. So this allows us to reason from longer videos, especially for retrieval purposes. Yeah, and there are other techniques as well, but standard way of concatenating visual tokens with text tokens for longer videos. We do have challenge in terms of compute and squared complexity, as you mentioned, and via cross attention, we find this as a good solution.
You mentioned that the benchmarks are lacking in their vision centricity. Can you talk a little bit about the benchmarks, the key benchmarks for this problem that you use? And did you explore any of the newer vision centric benchmarks?
So benchmarks like Science QA, which has an image, high school science related questions, AI2D, they generally uh, we can for most of the questions, even if you don't look at the images, you can respond to them. So more lately, people have come up with new benchmarks like CV Bench, which makes sure that the question cannot be answered without looking at the image. For example, which object is closer, person mm, or the table, right? So for that kind of information, just relying on the language model's parametric memory, you can't respond to that. You really have to look at the image and then respond uh, uh, to the question. So these kinds of questions where you don't need to articulate the answer in terms of language, but your answer might be short and crisp, but you have to look at the visual data. Uh, those are the benchmarks that really, or spatial correspondences. Like we are given paired images, and we say um, on one image we have 4 points, and on another image A, B, C, D, and another image we have 1 point, and we say which one of the 4 points this point in image B corresponds to. So for that, you have to really look at the visual data. So uh, these are uh, uh, these are the benchmarks basically that we need to pay attention to make sure that vision uh, is not being ignored. We are really solving the vision centric problems.
Earlier in introducing this challenge, you talked about object hallucination in VLMs. Do you think of object hallucination as like a general failure mode that contributes to like all of the problems that VLMs have, or is it, a particular failure mode and um there are particular benchmarks that you looked at to look at hallucination performance?
So, of course, we looked at a particular hallucination bench, which is a benchmark, but uh, I guess it's a problem in the sense that if you ask a question, uh, uh, for example, how many cats are there in the image? If the cat is sitting in front of a mirror, right? So it would hallucinate and respond to two. Or if there is a scenario which is very common and you ask a counterintuitive question. So we know elephants are of a certain color, uh, but if you provide a counterfactual example like an elephant painted pink and you ask what's the color of the elephant, so it would uh, hallucinate and say so those kinds of scenarios where uh, I guess um, uh, we can see and study if the model is hallucinating or is it really paying attention to the vision information.
Yeah. Okay. Yeah. That the way you answered that kind of gets at, I think, a thought that was underlying my question, and that is like when there's a cat looking in a mirror, and the model says two. Um, is that is that hallucination, or is that some other kind of error? Like, or when the elephant, when it says the elephant is gray, but the image says that it's a pink elephant in the image. You know, I guess it's maybe I'm probing at like the definition of hallucination in a VLM context, but and you kind of suggested that maybe one way to define hallucination is if it's not attending to the visual tokens and it's attending to the textual tokens only. Um, but it suggests to me that there's maybe a more granular way to talk about error modes in VLMs where hallucination is not necessarily the same as relying on textual what it thinks it knows from text parameters, and maybe there are other ways to like kind of chop up these errors that might be insightful.
That's right. So think of scenarios like which object is closer to the camera, who is on the left of a person, or from third person's perspective, like if there is an image, there is a car, there is a motorcycle, and then there is a person, and we ask a question: if you are a motorcycle and you're looking to your left, what do you see? So those are, I guess, there are different granular levels to which we can break down to the problem, and maybe hallucination is not the right word to kind of club them all together. We are borrowing that term from language community, but we are kind of identifying challenges related to them, and then um, seeing if current VLMs can tackle that. Counting is another one. So counting is an integrative reasoning problem, um, and we see that current foundation models struggle at that. Um, and also iterative reasoning or multi-step reasoning. So, for example, if you took an image of uh, the price board of a gas station, and it says Supreme is $3.40 per gallon, and you say, I want to fill how much of fuel I'm going to get for $50. So that's more of iterative multi-step reasoning problem. Like it first needs to OCR, read at the visual data, then extract that information, go back, reflect on your question, and then do this compute and come up with a response. So currently, we just do inference in a single step in an end-to-end manner. We're given an image and a question, and we just start spitting out tokens one at a time. So you're right. Like uh, granular definition of these different problems, they might not all club under hallucination as such to say, but yeah.
Yeah, and as you're responding, I'm also kind of thinking about it from the text perspective, and like it's probably true that there's a whole set of like reasoning failures and other kinds of things that we kind of lump under hallucination, in the sense that somewhere down there the model is making up something that isn't grounded in the reality of the prompt or the input, and that's like the foundational cause of the problem. And so that's from that perspective the term makes sense here as well.
Yeah, that's true. That's right. So basically, we try to identify all those problems, and uh, then a common approach has been people identify a limitation, go back, collect data around that, include that data as part of visual chain of thought reasoning, and that helps us tackle that problem. But yeah, you're not basically grounded in the visual input, or it's just outside the reality. Yeah. So mm,
Awesome. Awesome. Let's switch gears to another paper that you have at NeurIPS on generalized contrastive learning, better search across text and images. Talk a little bit about the setting and the motivation for this paper.
yeah, sure. So as you know, Qualcomm has a strong interest in mobiles, and one of the key use cases in there is we have a gallery of images and we want to retrieve. So generally, we do retrieval based upon text query. But there are scenarios where a query can be composed or it can be fused. From that, I mean, it can be composed of both text and visual information. So, show me images, all the images of a person looking like this, for example. So, our query is both image and text. So, what we see is for scenarios where our either query or key is composed, it's not single, either text or image. We see that the current vision language contrastively pre-trained model, like clip-like models, they struggle, and there's a clear reason for that. Why do they struggle? So this paper basically tries to tackle that problem. So it tries to tackle composed multimodal retrieval.
And you said there's a clear reason why they struggle. Why do they struggle?
So if you see the way they are trained, so we have a bunch of images within a batch, and then we have corresponding text descriptions. So images go through the image encoder, text descriptions are encoded via the text encoder, and then we have a shared embedding space where both image and text speak to each other, and in this space we compute similarity of image and text. And within a batch, and then we make sure that image text pairs corresponding to the same should be closer together, and if they're different, they should be separate apart. That's how we train these models.
Got it. So there's no component of training where we're corresponding text and images in the same space.
Exactly. So uh, the general way people try to tackle this is they collect training data of triplets where if you think of query and key, query can be image text and key can be image, or it can be image and text plus image. Query can be image and key can be text plus image. So we can think of different possible combinations of that. So a general way people have been tackling this problem is collecting this triplet data of different possible combinations and then training the model with that newly collected data. But this has its limitations, like it's laborious, it takes time, and it takes lots of effort, manual effort. So what we thought, what we came up with in this paper is, let's not collect any data. Let's see if we can do something in the loss formulation. So the loss is basically applied. So on one axis we have all the images in a batch, let's say n images, and on the other axis we have n text descriptions. And then we compute similarity between these text and n images, and we apply the loss on this n by n matrix. So now what we try instead of this n by n matrix, we try to change the possible combinations. So we say we have image embedding, we have text embedding, and we can get a fused image text embedding by just doing simple fusion. Uh, so now we have three embeddings: image text and image plus text. And we can come up with multiple combinations. Like we have three and we want to select two. So we can come up with multiple combinations of those, and then we can compute similarity between those multiple combinations and reformulate our loss based upon those similarities that come from uh, combinations of two from three different options: image, text, image plus text. And this helps us generalize uh, to scenarios where our query and key can be any modality, any single or fused.
And so in the same system, you mentioned this triplet and you've got different permutations of this triplet. Are you training only on a particular permutation or are you training on all of the permutations of this triplet?
We are training on all possible combinations of the triplets because for us it's very easy to get those. Like we don't have to collect any data, right? And we gain in terms of generalization to unseen scenarios. And one of the things we observed as kind of an evolving characteristics of this loss formulation was that it even evolved and generalized to videos. So there is a benchmark called composed video retrieval, COVR, and we do evaluations on that. So even though we did not train on the video data, but since our queries were both images or image plus text or text, and same goes for keys, we saw that we were able to generalize to those scenarios as well.
And is a way to think about this in the context of like the traditional clip approach is that it's like adding dimensionality to the embedding space?
That's right. So it's just enriching the embedding space more, and um, it's just instead of just vision and text, it's enriching it with other modalities. But I guess this problem is still not solved. Especially, we see that in the case of clip or the follow-up variants of clip, the text encoder is kind of weak. Like it has seen a specific distribution of text, which is just description of images. Language is much more richer. If we have information like verbs, action, and so on, so we see Clip does a poor job on those. So I guess a principal way that we are like a way that could tackle this is move away from that and maybe do retrieval in the embedding space of a multimodal model where what we were discussing earlier, um, you have a language model which is much richer in terms of text, and you also have a text vision model, and you just try to align these different modality combinations in those embedding space. Basically, your language model or text encoder is now a better text encoder, which is a language model.
Do you see that, or are you raising that as a future direction, or is it something that you've tried, or is it something that you're foreseeing as being, difficult because of some of the challenges that we raise?
I'm foreseeing it as a future direction, especially if you want to retrieve cross model information in the form of text and image both, then I guess like a future um, embedding space of a multimodal model is promising compared to embedding space of a clip-like model. Clip-like model is also a multimodal model, but in my definition of multimodal model here is embedding space of vision language model, like where the language model is a true LLM. It's not a text encode like clip, right?
Now, when you started off describing the problem, you reference wanting to do this in a mobile environment. I'd like you to talk a little bit about some of the results you saw and how they enable running in a mobile environment, but also, in talking about going from a clip type of model to a VLM, you're adding a lot more complexity, and that's kind of against your odds of running in mobile. So, talk a little bit about what you see there.
You're right. Clip has its benefits in being efficient. It's like 300 million, 400 million visual encoder and 100 million, 125 million to be precise text encoder, which is very efficient. And um, on mobile, we can easily implement it, and by consuming very little power, it can enable this composed retrieval scenario. Uh, for VLM, vision language model, where we have a language model and a vision encoder, we are increasing the memory. But interestingly, what we found is that even the small language models, it is small SMOL LM from Hugging Face. They've trained. variety of small language models, sub 1 billion parameters in 0.125, 0.25, 0.375 billion, very, very small language. So even its embedding space is good enough for retrieval. At least our initial experiments suggest that. And we are mindful of the additional memory and compute that it brings in. But uh, I guess the challenge is going to be how do we tackle it going forward.
And so, with regards to the approach proposed by this paper, this generalized contrastive learning or GCL approach, what what is the computational impact of that?
I would say it doesn't bring in any additional compute. Uh, we just need one single forward inference pass of both. Once we're building the database, as well as once we're querying, we just need one forward pass of the query through the relevant encoder, image or text encoder. And as such, we are not changing the architecture of the model. Um, it's basically a better way to train with a better loss formulation. So, in terms of inference, there is no additional compute.
And in terms of benchmark performance, what are the key benchmarks and what kind of performance results have you seen?
So we have seen gains, significant gains on um, massive multimodal embedding benchmark, for example, MMEB, and then there is another benchmark which is composed of multiple other benchmarks. So we have seen key improvements in those compared with other SOTA approaches. In some cases, quite significant. But another interesting aspect is if you see the results, still for some of the different permutations that we were discussing earlier, the results are not. At a point that we can really use. We can use these in real life. My point being, this is still an open problem, and we we need to push research on that front.
Another paper that we wanted to dig into is called MultiHuman Testbench, raising the bar for multi-person image generation. Uh, and when we talked a little bit about the motivation here, I don't know that I realized that uh, generating images with multiple people was such a challenge for these models. Talk a little bit about that issue.
Right. So even if we consider a single person, so I think a common use case is I have my images, my portrait images or my selfies and so on, and I want to personalize them, right? Um, so a challenge we see is once we personalize those images, it might generate an image in the scene I have asked for, but it loses my facial identity. It might generate a person which doesn't look like me, and humans are very good at kind of identifying those kinds of artifacts that it doesn't really uh, uh, look like the person you're trying to generate. But even a bigger challenge is if we if we do conditional generation based upon our condition being two, three, or four people, and we want to generate them doing an action or in a specific scene, there we see that facial identity information of the subjects that we want to generate, the conditional subjects, it's lost quite a bit. And even we see, I mean, once we benchmarked the proprietary foundation models, we see that they can't get beyond certain number, beyond three or four. They are unable to get accurate number of subjects you have asked it to generate. If there are five conditional images you want to generate, it might generate three or four, or it might not generate all five in there. So uh, we realize these kind of limitations, and then I think there is a need for us to push research in this direction. And a low hanging fruit for us is to come up with a benchmark that can help community and drive and track progress on this open research problem. So this is where this benchmark comes in.
To be clear, what you are providing first and foremost is a benchmark. I'm imagining this has a lot of images or text prompts that aim to generate multi-person images.
We have benchmark, and we also propose a solution, a preliminary solution to tackle this problem. But primarily, it's a benchmark. So we have the benchmark contains for tests. It contains we are suggesting 5,500 different individuals to generate 1,500 test samples in different scenarios with different actions and so on. And we are working on extending it beyond. So we come up with complex with prompts where humans are doing different actions, and then we also propose different quantifiable evaluation metrics, like count accuracy being one. And how do we get those metrics? Like we detect faces and then we count them. And if we want to preserve facial identity information, what's a quantifiable metric for that? So we detect faces, we pass them through a facial discriminator model, which has been trained to discriminate faces, and then we compute the embeddings of the generated face versus the conditional face, and they should be above a threshold for us to declare that it's the same person. And then we also have another metric which is MLLM as a judge, and another metric which quantifies HPSV2 score, human perception score, which is a generic score to suggest how much is the prompt adherence to the in the generated image, and how is the visual fidelity of the generated image. So um, basically, we provide test samples, we come up with challenging scenarios, and then we also provide quantifiable metrics to gauge the performance of a model on on the task. And that's one side of it. The other side is we also looked into how we can solve this problem. So uh,
I'm imagining that some of your solution is taking your metrics and building them into your loss function when you're training.
that's an obvious thing to do. But another thing that we came up with, and I think it's interesting, is um, once you're generating multiple people, and if you think of, like, we have multiple tokens, and the way attention is applied is either causal, that your, your future tokens only looks at the past tokens, uh, and or it's bidirectional. But in this case, if I'm generating images of two people, I don't want tokens of one person to attend to tokens of another person. That's a very simple intuition. And why? Because there would be some kind of identity leakage in doing so. So we basically define these kind of islands or masks where token of one person only attend to tokens corresponding to one person only attend to that person, and tokens correspond while generating an image, tokens corresponding to every person just attend to that particular person, and they don't kind of cross attend to other people being generated. uh, this kind
And the models are able to do a good job of tracking that.
we can define
Seems like a finer grain constraint than is usually placed on the model.
that's right. So we have to we have to define that, and we can do that fairly well, and we show some quantifiable results that this does improve, and it helps us tackle the challenge to some extent, but largely it's still unsolved. And I guess the recent version of Gemini and Nano Banana, which was released just
Nano Banana Pro just last week or so. Hmm.
they one of the thing they seem to tackle is in their blog post I was reading is this particular problem. So
Multi-person in particular or facial continuity in general?
I think and they portray as multi-person, multi-subject, or multi-object personalization. So once you want to generate an image conditioned upon multiple different subjects and objects, how do you preserve their identity? So it's more of a generic version of the problem.
And going back to this theme of efficiency, does the approach that you propose, or like how does efficiency play into either your solution or the benchmark more broadly?
Right. I guess in the solution, w- uh, we are not involving any additional compute. It's just that we are redefining the attention masks, which is a trivial operation. And it kind of helps. Like instead of attending to all tokens, we can skip quite a bit. But it doesn't introduce any additional compute. The other part is we could do personalization by just fine tuning the parameters of model with a low rank adapter or something like that. Uh, but that's prohibitive. That's compute prohibitive, especially in case of mobile. So this personalization that we are talking about is basically inference only. Like, okay, you do training, but once you deploy the model, you're not optimizing it anymore. So the model should be able to generalize to any person's face, and it should be able to generalize and generate or personalize to any facial images. So at inference, we are not we don't need to like learn any adaptation parameters. So uh, that's one key aspect of this approach. Like if you see dream booth like approaches, they have to we have to learn uh, uh, a dedicated adapter network to personalize. And in this approach that we are proposing, it's inference only.
Awesome. As is usually the case, Qualcomm had a ton of papers as well as demos at NeurIPS. Are there any other papers that you would want to highlight?
Qualcomm has a very strong presence at NeurIPS this year. We have, I guess, 17 papers, and if I'm not wrong, something like 9 different demos, which make up of 50% of the expo demos, close to 50% of the expo demos at NeurIPS this year, which is, I think, which is quite nice. So we have quite some interesting papers. Some of the ones that come to my mind is um, LLM inference from long context. I think it's called key diff. They have they have a very interesting intuition that if you diversify your keys, this corresponds to the keys that are attended to most during inference, and this can enable us to do KV cache eviction, and it can enable us to do it in like as the new data is being pre-filled, KV cache pre-filled. We can do this KV cache eviction on continuously. So I guess that was a nice work to enable inference from long context. Then there was another work on LLMs. It's called Omni Draft. So basically, it enables you to transfer the draft model trained for speculative decoding across different families of networks. And they I guess they show it on Llama 3, Vicuna, and Quen. Models, and they come up with some with an interesting approach, n-gram cache, where uh, uh, the difference the main difference is across families of models we have different tokenizers, and how do you make sure that one tokenizer corresponds to another one, and n-gram cache basically bridges that gap. And then there are apart from GCL and multi-human benchmark, there are other. I guess there is a work on streaming multimodal reasoning. And they tried. So current language vision language models, they struggle to basic basically they don't know when to stay silent and when to speak. So think of like if I'm doing cooking, or if I'm doing an exercise and I want my model to be my coach or to help me. And if I do a mistake, it should tell me. If I'm doing okay, it should tell me. And if there's nothing interesting happening, it should just stay silent and observe. So currently, the way these models are trained, we upload an image and a question, and it has to respond. And then we ask another question, and it has to respond. So can it basically stay silent when it has to, and interject when it has to? So this kind of interactive reasoning. Um, I think it's called Qualcomm cooking benchmark, interactive cooking benchmark, something like that. So that's an interesting work on that. And on demos, I guess one of my favorite is video generation. So we have mobile diffusion transformer generating 48 frames in under 8 seconds on a mobile phone, which is quite nice. And then there is a single step diffusion based image editing demo. It's
Sounds like Swift Edit,
Swift Edit. That's right.
which I covered in a conversation with Hung Bui on the podcast recently. That was developed by his group.
That's right. And we will show it at NeurIPS this year. And then I guess there is another demo on retrieval from long videos. And there are computer vision demos, traditional computer vision, like open vocabulary detection and segmentation demos. And I guess there is a demo on 3D Gaussian splitting as well. So we have an interesting lineup of different demos at NeurIPS this year.
Awesome. Well, enjoy the event. It is coming up very quickly, and maybe enjoy your Thanksgiving as well. It was great to connect with you, Munawar. Thanks so much for catching us up on all of Qualcomm's work at NeurIPS this year.
Thanks, Sam, and it was nice talking to you, and I look forward to our next conversation, hopefully.
Same here.
All
Thank
right.
you.
Thank you. Have a great Thanksgiving.